All right. Can you guys all hear me? Yes? No? Someone? Oh, yes. Okay. Thank you for responding. Well, thank you for joining at 9 a.m. on a Sunday. So let's hopefully just whiz through the rest of chapter two, and I'll let you guys go and enjoy the rest of your day. So let's just first slightly go over what we went over in the previous class because we started talking about how to name different types of compounds, and we were able to find out that we follow a specific set of rules called the IUPAC rules. And so when we look at these types of alkanes, we're first going to be able to see those that don't have any branching and those that do. Well, if we basically have those molecules that aren't having any branches, which we call substituents, we're basically going to just look at the longest number of carbon chains that are present. And we're going to be able to find out that in majority of the cases, they're going to have a specific prefix that we have designated. And if they are an alkane, we're going to just end with an ane. And so if we look at then examples of molecules that do have the presence of substituents, then first of all, we're going to do the same thing. We're going to try to find out the longest continuous carbon chain. And then in this case, it's going to have 5 carbons, which means that it's going to end with something, pentane. Now, we're able to see that it only has a presence of one branching or one substituent. And in this case, because it's only a CH3 group, which we basically call a methyl group, we're going to just have the methyl that's going to be added to the parental name of pentane. But there's one thing that we need to do, which is going to be identifying which location of the carbon the substituent is bonded to. And so when we try to find out how to number the chains, then we want to be able to give the substituent the lowest number possible. And so if we try to give the lowest number possible to where that substituent is, we're able to find out that it's going to be numbered from the left to the right side, which is why the methyl group is going to be present on the second carbon. And so as a result, the ultimate name is going to be called 2, which is going to be designating where that substituent is, followed by a dash, and then we're going to designate that specific substituent and then follow it off with a parental name, okay? And if we have multiple substituents then, in those cases, we're going to basically list all of these substituents in an alphabetical order. Now, when we write the alphabetical order, we're not going to take into consideration any of the prefixes that we basically use like sec or tert or neo, okay? And even those like di, tri, to be able to tell us how many of these substituents that are present are also not going to be considered when we try to alphabetize the specific substituents when writing the IUPAC nomenclature. So we now want to talk about the major type of substituent that's going to be present other than just a methyl group. And so those are going to be those of the alkyl groups. And so when we try to name these alkyl groups, it's going to be very similar to when we name these alkanes, except instead of ending with an ane, they're now going to end with an il. And so instead of ethane, if we have a 2 carbons long substituent, we're going to be calling it an ethyl group. And if we have a 7 carbon chain that's going to be a substituent, it's going to be a heptyl group, and so on and so forth. Now, when we look at these alkyl groups, the important thing to note is that specific carbon that is attached to the rest of the family chain. And we want to know, with respect to this specific carbon, how many other groups or how many other carbons are going to be bonded to it. And so that's basically telling us the substitution pattern at that specific point of attachment, which in this case is the carbon. So how many of these bonds that it's making to that specific major carbon is going to be substituted by something other than a hydrogen. And so in this case, we have that carbon that's going to be bonded to one other carbon. And so it's going to be called a primary alkyl group, and the substitution is going to be primary. So it's mono substituted. Now, if we look at the next molecule, we're able to see that this is also an alkyl group, but that specific carbon that's the point of attachment is now bonded to two other carbons. And so the substitution pattern is going to be di-substituted, which we basically just kind of show it as so. And it's going to be a secondary carbon. And so we can call it also a secondary alkyl group. And if we have this major carbon that's going to be bonded to three other carbons, then it is going to be tri-substituted, and it's going to be a tertiary alkyl group. And so by knowing the substitution pattern of these alkyl groups, we can actually use this another way to be able to name these substituents. And that's basically when we utilize a common name. And so normally, when we have a alkyl group like so, the IUPAC rules tells us that the carbon that's directly attached to the family chain is going to be given the number 1. So it's going to be carbon 1. And from here, we're going to do the same thing like we did with alkanes. We're going to find the longest chain possible, which is going to be 1, 2, 3, 3 carbons long. So it's going to be, in this case, instead of a propane, a propyl group, because it is an alkyl group that's coming off of it. And we have the first carbon attached a methyl group. So it's going to be a 1-methyl propyl group. But because this is pretty long, and if you want to follow this rule to be able to name a compound, it's going to become very, very wordy. And so a common way to be able to name this specific alkyl group or the substituent is basically to say it is a sec-butyl, because that carbon is going to be a secondary carbon because it's attached to two other carbons, so it's di-substituted. And with regards to the total number of carbons that's in this alkyl chain, it has 4. And so it's going to be a butyl group. Now, when we look at those specific alkyl groups that use the prefix iso, this is going to be confusing for some students. So make sure you listen to this part. So when we talked about iso prefix previously with regards to alkanes, we were able to see that it means an isomer of a specific compound. And so if we looked at isobutane, for example, it would basically mean that it's going to have 4 carbons and it's going to have 1 methyl group, and that's why it's going to be a isomer of butane with 1 methyl group, and the longest chain being possible being 3 carbon long. Now, when we talk about it with regards to alkyl groups, we usually use the iso to define it as when we have 1 methyl group that's going to be extended off of the alkyl chain, but it's usually going to be at that end of that chain. So if we have a sec-butyl group, we're able to see that in this case, we have the specific methyl group coming off of the first carbon, which is why we use sec-butyl. However, let's assume that we have a compound or an alkyl group that actually has this methyl group that's not attached to the first carbon, but on the second carbon. Now, in this case, the carbon in the primary point of difference is going to be only attached to 1 other carbon, which means it's going to be primary. So in this case, we actually have a methyl group that's extending from the second carbon and therefore is forming this type of structure towards the end of that specific alkyl group. And so anytime we have this type of methyl group that's extending at the very point of the alkyl of the substituent, we can use that prefix iso. However, we mostly use it with regards to isopropyl, and we don't use it in many other cases, but you will be able to see that in some cases like so, if we do have a very long alkyl chain that has this type of one methyl group coming off of the ends of that substituent, we can also use iso, however many carbons, as that specific naming as a common name. So you have to know the difference between sec-butyl and isobutyl, because they're going to definitely have differences with regards to where that methyl group is present. Can you guys still hear me? Okay. And now, when we looked at those alkanes that have not just a short methyl group, but branched alkyl groups, and we have multiple branching, we were able to find out that in those cases, we do use alphabets to be able to identify which specific substituent is going to come first. And with regards to alphabetizing, like I said, prefixes like di, tri, tetra, or sec and tert aren't going to be considered, but iso is actually going to be considered when alphabetizing with regards to the IUPAC group. Okay, so that's the only one that's going to be considered. And then every other prefix, like such as these, are not. Now, let's go on to learn about cycloalkanes and how to name these. So, when we look at cycloalkanes, first of all, their molecular formula is going to be CnH2n. So this is going to be exactly the same as when we have the molecular formula of alkenes, because alkenes likewise had CnH2n, whereas alkanes had CnH2n plus 2, and alkynes had CnH2n minus 2. So alkenes and cycloalkanes are going to have the same type of molecular formula. So we have to realize, though, that cycloalkanes always needs to have more than 2 carbons to be able to form that ring. And so we're able to see that the smallest cycloalkane is indeed going to have N being 3, and it's going to be called cyclopropane. So we were able to see that for alkanes, we name them by having the number of carbons that are counted. And in this case, it's the same, except we just all we're going to be doing is basically adding the prefix cyclo towards the front of that name. So when we look at these cycloalkanes, then how are we going to actually find out how to add these substituents or name the substituents that are going to be bonded to them? Well, it's going to be the same because most of the times we are going to be seeing these alkyl groups that are attached to these cycloalkanes. But then the problem that we have to ask then is which specific point of that cycloalkane is going to be numbered 1. So when we look at this example, we're able to find out that we have situations where we only have one substituent that's going to be attached to that cycloalkane. Well, in that case, that first point of difference is indeed going to get the lowest number and therefore is going to be given locant number 1. So in this case, we have the parental structure being a cyclopentane. And attached to it, we have an alkyl group that's going to have 2 carbons in total, which makes it an ethyl group. So in this case, it will be ethyl cyclopentane, and we don't have to really write 1 because it's basically obvious that this is going to be that first point of difference. However, if we basically have multiple substituents then on multiple sites of that cycloalkane, we're going to be basically finding out how many of these substituents can have the lowest locant number possible. So if we try to give this ethyl group locant number 1, then we can try to give this this specific carbon locant number 3, which in that case is now going to have the ethyl group, all of the locant positions being 1, 3, 3. However, if we actually name it the other way and give this specific carbon number 1 with 2 methyl groups and this specific carbon, then carbon 3, then the locant positions for the entire molecule is going to be 1, 1, 3. And so out of these two, we want to be able to have most of these specific substituents have the lowest locant number possible, which is why we're going to basically number this carbon as 1 and go in a clockwise to give this specific carbon that bears that ethyl group locant number 3. However, we have to realize that we have 2 methyl groups, so it's going to be named dimethyl, and we have 1 ethyl group at position 3, so it's going to be given the name 3-ethyl. And when we try to write the entire molecule's name, we have to consider the entire family chain, which is going to be 6 carbons long, and it's a cyclic structure. So it's going to end in a cyclohexane. Now, we're able to find out that we have to name these substituents in alphabetical order, and we're not going to consider the prefix di, which means it has to come with 3-ethyl first, followed by 1,1-dimethyl cyclohexane. Now, we have situations where we actually do have a presence of cycloalkanes that are bonded to alkyl chains, but if we actually count the number of the carbons in the alkyl chains, they're actually going to have more carbons there than the number of carbons in the cycloalkanes. So the example shown below shows us that the alkyl chain has 5 carbons. The cycloalkane has 4 carbons. So in this case, we're actually not going to consider the cycloalkane as the parent. We're going to consider specifically in this case, the alkyl group or the alkane as the family group or as the family name because it has more numbers of carbons. And so as a result, instead of ending with a cyclobutane, we're now going to end with that alkane name, which is a pentane. And then we're going to consider this cycloalkane as a substituent. And likewise, because this is a substituent on the alkane, we're going to try to number the carbons to give it the lowest number possible, which in this case won't matter from the left or the right. And we can see that it's on the 3rd carbon. So it will be called 3-cyclo and then butyl pentane. Okay. So if we try one of the questions which is given here, let's actually try both. So in this case, we have a compound that's going to have 2 methyl groups at one position, and we have 1 substituent on the other carbon. So it is natural to try to give the lowest locant number possible. Therefore, we're going to be numbering this carbon as 1. And then we're going to go in a counterclockwise manner, which is now going to give this locant number 4. Now, if we look at all of these substituents, then we have, first of all, 1,1-dimethyl. And at locant 4, we have 4, and we can have 2 ways to be able to express this. We can either use the common name, which is going to be isopropyl, or we can use the IUPAC nomenclature, which is going to be looking at the longest chain possible of the alkyl group, which is 2 carbons long, which means it's going to be an ethyl group. And to this ethyl group, we have a methyl group that's attached to the first carbon. So it's going to be a 1-methyl ethyl group. So we have 2 ways to be able to express this. So let's try using the common name first to be able to write this. I said that the iso is indeed a prefix that's going to be considered when alphabetizing this specific type of compound. And so if we look at the entire number of carbons in this cycloalkane, it has 10 in total. So it's going to end in a cyclodecade. So if we use the common name, we're going to be able to find out that it's going to be iso I that comes before the M, so it's going to be 4-isopropyl dash 1,1 dimethyl cyclodecane. Now, if we then try to use the IUPAC nomenclature to be able to explain this substituent, then the alphabetizing is going to be different because they're both going to start off with an M. And so in this case, we're going to try to give the locants a number and consider that when trying to write their name. So in this case, we have 1,1 that's going to be in front of, that's going to be in front of the locant position of 4,1-methyl ethyl. And so we're going to write 1,1-dimethyl, and then we have to write that this entire alkyl group is on the 4th carbon, and the entire alkyl group is going to be written in parentheses just to not be confusing when looking at the entire name. So it's going to be 1-methyl ethyl, and then cyclodecane. And this is why we would prefer using this type of common name if it's possible, just because it makes it much more simple to use. Now, if we look at C, then we have 2 cyclohexanes that are going to be bonded together. In this case, they're going to be completely equal with regards to the number of carbons. So either one can be a substituent. So it can be cyclohexyl, which is going to be one of them, and then cyclohexane as the other, that's going to be the parent. Now, let's look at functional groups. Now, when we look at what functional groups are, they're going to be any type of substituent, except it's not just going to be composed of carbons and hydrogens. Instead, it's actually going to have heteroatoms or multiple bonds. And so a lot of the times when we talk about functional groups, they actually have similar chemical properties within these different compounds. So we're trying to group them together based on their function. And so when we try to name these compounds that have functional groups, we usually try to write them as alkyl derivatives of these functional groups. So what does that mean? We're going to actually have the functional groups be the parent for that specific molecule because it determines the type of chemical reactions or that function that that specific molecule is usually going to have. So if we look at one example, we can try to look at alkyl halides. So it's going to be those of the alkyl groups that are bonded to a halogen atom. So an example here is ethyl bromide. And so you can see that in naming these compounds, they're going to have that specific halide, which is going to be the parent for this specific compound. And then we're going to consider that alkyl group as a substituent. And because it has 2 carbons, it's going to be ethyl and then bromide. Now, if we look at this compound on the right, it is also an alkyl halide and it has chloride as that halide. Now, in this case, the alkyl group is going to be tert-butyl because that specific carbon that's bonded to chloride is basically tertiary with regards to its substitution. So this is a common name with regards to writing for this type of alkyl halide. Whereas if we did try to follow the IUPAC nomenclature, then we would have to basically look at the longest chain possible and then write that specific methyl groups that's coming off of that main carbon. Now, other types of molecules with these functional groups, a main example that will continuously come up are alcohols. And so if we look at alcohols, there's going to be the functional group in this case, which is a hydroxyl group, which ends with then oxygen and hydrogen, and they're going to be bonded to an alkyl group. And so the example that they're showing us here is we have that hydroxyl group that shows us that it's an alcohol, and we have isopropyl, which basically looks like this. And if we look on the right, we have a cycloalkyl group as a substituent coming off of that hydroxyl group. And so it'll be cyclopentyl. And then in this case, if we have a hydroxyl group, the name is going to end with then alcohol. Now we're going to briefly look at where then do these alkanes or these cycloalkanes come from? And most of them are indeed going to come from petroleum deposits, which are basically petroleum that's going to be found under the ground and the sea. And so this is going to be where all of these alkanes, as well as other hydrocarbons, are going to come from. Now, petroleum is a much more broad term to be able to talk about this type of oil. But then if we get a little more, or if we look more closely at petroleum, it can basically be distinguished into crude oil or petroleum oil. And so when we look at crude oil, it's a little more specific than petroleum. And we can use the crude oil to be able to basically get all of these different types of compounds that are all going to be basically alkanes or hydrocarbons. Now then, are we only getting alkanes from petroleum? And the answer is no. We can also find that there are biological sources of these alkanes, and it's going to be not very abundant, but they are present. For example, if we look at pentahosane, which is basically when we have 25 carbon long alkanes, they were able to find out that it's going to be present in the coverings of many insects. And the major role of having this type of alkane for them is to prevent the loss of water. And if we look at hentriacantane, they were able to find out that for this type of alkane, it's found in beeswax and other waxes. And when we look at cycloalkanes, it's not found in abundance in nature. However, there are cases where we do find them. For example, if we look at hopane, they were able to find out that they are part of the bacterial cell membrane, and so it could be found. So it can be found in usually petroleum deposits, but there are also incorporated in nature as well. And you don't have to really know, just know how to basically have the molecular formulas for alkanes, alkenes, and alkynes, and you'll be fine. And I probably won't give you ask you a specific name of an alkane that over exceeds like 15, okay? Now, let's look more into the physical properties of these alkanes and cycloalkanes. Now, when we try to look at these physical properties, we first have to talk about intermolecular forces. Now, when we look at the terminology of intermolecular and intramolecular, you have to find out that they are very different. When we talk about intramolecular, this is going to be within the compound or the molecule. So when we look at intramolecular, it's going to be between these two atoms that are already having a bond or an association with them. Whereas when we look at intermolecular forces, it's between different molecules. So for example, water molecules with other water molecules. What are the forces that are going on in between these two different types of molecules that are in a solution, for example? So if we look at alkanes then, we're able to find out that they usually have nonpolar carbon-to-carbon bonds, and they're very, very weakly polarized carbon-to-hydrogen bonds. And so overall, the entire compound can be seen as nonpolar. So if we have these two nonpolar compounds, or these two alkanes then, that are present near one another, they are actually able to have instantaneous dipoles. And the reason for that is because when we look at all of these electrons, they're not just going to be fixed in one area of that molecule. They're constantly moving around, which is why when they're basically close enough, they can have this type of partial positive charge and partial negative charge at one given instance. And therefore, that's basically that's when we usually talk about with regards to these intermolecular forces. And so when we have, for example, an instantaneous dipole, they can basically cause a dipole in other molecules, and they can be attracted towards one another. And so if we have this type of dipole-dipole that's been induced among one another, we usually call that van der Waals interaction or London dispersion forces. So when we look at three types of van der Waals forces, but to be more exact, we would usually just try to generalize this as intermolecular forces. There's three major types. The first one is when we have a dipole-dipole interaction. And in this case, we have one molecule that is polar and another molecule that's going to be polar. And that's why they have dipole moments. And so this is going to be the major type of interaction shown during hydrogen bonding, because when we look at hydrogen bonding, for example, in water molecules, we're able to see that each water molecule is going to have a dipole, and that's what allows them to have that type of attraction between one pole and the other. And so this is going to be the strongest type of intermolecular forces that are present. Now, the second type of intermolecular forces is going to be when one does have dipole and the other is actually going to be induced because of the presence of this polar molecule nearby. And so as a result, in this case, it's going to be a weaker type of interaction compared to dipole-dipole, but it is going to be stronger than the third type of interaction, which is the induced dipole-induced dipole. So induced dipole in this case is going to be between usually nonpolar compounds and other nonpolar compounds. But as a result of this instantaneous positive and partial negative charge due to this type of electron movement, they're now going to have the other molecules nearby also exhibit that type of dipole pattern. And as a result, this is going to be one of the weakest intermolecular forces that are present. And a lot of the times, this induced dipole is what we call London dispersion forces or van der Waals interactions. And so when we look at most of these alkanes, they usually don't have any dipole moment, and that's why they're only going to be undergoing this type of induced dipole attractive forces. So now, if we know this type of intermolecular forces between alkanes, we're able to find out their boiling points as well as their melting points. So if we look at those alkanes, and we try to understand this with regards to boiling point, if we have these alkanes that are now going to be basically having this type of instantaneous induced dipole and induced dipole with regards to one another, they're able to basically have weak interactions with one another that hold them together. And now, if they basically want to find out the boiling point, we have to continuously increase the temperature to be able to break these types of intermolecular forces. So we're able to find out that if we have those alkanes that are more longer compared to those that are shorter, they're not going to be involved in many more of these intermolecular forces or these van der Waals interactions, which is why the longer the alkane is, the higher the boiling point is going to be. Now, when we talk about this with regards to surface area, it's basically what it is. If we have a higher surface area, then that means they have much more area to be able to undergo these types of van der Waals interactions. Which means if we have those alkanes then that are having branches or that have this substituents coming off of them, their surface area overall is going to be a lot smaller than those that don't have any branching, which means if they have smaller surface area, they have less area to be able to interact with other branched alkanes, which means there's less van der Waals forces around that specific molecule, which is why when we actually look at their boiling points, they don't need as high of a temperature compared to the linear alkanes to be able to achieve that boiling point. So, in summary, boiling points of alkanes are going to increase with molecular weight because it's basically needing more carbons or longer chains. And also when we look at branched alkanes, they're going to have lower boiling points than linear ones because they have a smaller surface area. And also, when we look at the melting point, it's going to exhibit the same type of pattern. When we look at molecules or these alkanes that are going to basically have increased number in carbons, we're able to also see an increase in the melting points as well. And also when comparing these linear alkanes and these branched alkanes, the melting points of these branched alkanes are also going to be lower compared to those that are linear. Now then, how about solubility in water with regards to these alkanes? We said that these alkanes are going to be non-polar in general, and that's why they're all held together by weak van der Waals interactions, which was an induced dipole interactions. Now, we said that there were 3 different types of intermolecular forces, and the strongest one was dipole-dipole interactions. And we said that water is indeed having this type of dipole-dipole interaction because they're basically forming hydrogen bonds within each water molecule. So if they're the strongest type of intermolecular forces within these types of out of the 3, then for a specific molecule to become soluble, they have to break this type of dipole-dipole interaction to be able to basically be soluble in them. However, the van der Waals interactions of alkanes with water isn't going to be strong enough to do so. And that's why when we look at alkanes, they're not really going to be soluble within water. And this type of phenotype or the effect is called the hydrophobic effect because they can't break the intermolecular forces between these water molecules. These non-polar alkanes are basically going to cluster together and basically form an aggregate to exclude all of the water molecules. Now, let's go over the chemical properties, specifically looking at a reaction called combustion. Now, when we look at alkanes, they're a very simple or reduced form of organic compounds because they only have carbon to carbon and carbon to hydrogen bonds. And they were able to find out that when we have these alkanes and the presence of oxygen gas, they're actually going to react very, very strongly. And as a result, they're going to be forming carbon dioxide and water. And this type of reaction where we have an alkane that's exposed to oxygen to give off this carbon dioxide and water is going to be called combustion. Now, when we look at this reaction of combustion, we're able to find out the enthalpy change, which is basically when we have the enthalpy or the heat content of the products subtracted by the heat content of the reactants. And so if the delta H is going to be a negative value, we know that this is going to be an exothermic reaction. And so if it's an exothermic reaction, then we know that this type of heat content of the reactants is going to be greater than that of the products. Now, when we actually look at this type of combustion reaction, it's able to tell us the stability of these alkanes. And so what they decided to do is look at this delta H, which is the enthalpy change, and basically have negative delta H be what's called the heat of combustion. And so the greater this number is, the more exothermic the reaction. And so more energy is going to be released. And so this is telling us that that specific reactant must have had a lot of heat or energy to give off. And so the reactant here that we're talking about is going to be that alkane. And so if we have a lot of heat that's going to be present in that alkane, that also tells us that that specific molecule is also very, very unstable. So when we actually look at the heats of combustion of some of these alkanes, we are able to see that if that specific alkane becomes longer and longer, the heats of combustion is actually going to become bigger and bigger, meaning that it's going to be much more unstable if that specific alkane becomes very, very long. Now, if we try to compare those specific unbranched alkanes as opposed to branched alkanes, they were able to find out that those that are actually branched are going to be much more stable compared to those that are unbranched. So if we look at hexane, they're able to see that this has 6 carbons. Their heats of combustion is 4,195. Whereas if we look at 2-methylpentane, which also has 6 carbons, this is basically when we have one methyl group coming off of that pentane, and therefore this is going to be an isomer of hexane. And you can indeed see that the heats of combustion, although minor, does seem to be smaller, which means that it has less energy than its linear chain. And so when we actually look at the reason why this type of branched alkane is more stable than its linear form of alkane, it seemed to be because of intramolecular forces that are actually affecting them. So if we look at intramolecular forces, I said that it's going to be between these specific atoms within the molecule. And so what researchers did was they were basically looked at the attractive forces between the positively charged nucleus, the negatively charged electrons. And so all of these types of repulsive and attractive forces, and they basically calculated how this is going to cause the heats of combustion to be changed. And they were able to find out that as these specific compounds become more compact and therefore branched in this case, they actually seem to be able to have an increase in the attractive forces between the nucleus and the electrons around it. And so as a result, this type of intramolecular force seems to allow for the heats of combustion to be lower, and therefore the stability of these branched alkanes compared to their linear alkanes seems to be much more stable as well. And also with regards to these intermolecular forces, we're able to find out that if we have these linear alkanes, they have a bigger surface area, which means that they're going to be basically having a lot of these intermolecular forces compared to these smaller branched molecules that are going to have less intermolecular forces as well. And so those do also play some minor effects in causing these branched molecules to be much more stable. But that's not going to be a major form of, I guess, heats of combustion being different. The major form is indeed going to be when we have increases in the number of carbons that are attached to that alkane. And so if we look at this figure here, we are going to be able to see this pretty frequently throughout this throughout organic chemistry. And this is a potential energy diagram. So it tells us how much energy a molecule has. So it tells us that when we have a specific type of alkane that's undergoing combustion, how much energy is going to be released during the process of this combustion to be able to form carbon dioxide and water. And so we can see that the linear form of octane in this case is indeed the most unstable form because it is the linear form compared to the most branched form of the same type of octane. And now let's talk about oxidation and reduction. Now, oxidation and reduction is pretty simple. I'm sure you guys have all heard of oil rig. Oxidation is loss, reduction is gain. And so what are they losing and what are they gaining? They're talking about electrons. So when we look at how to basically look at this type of oxidation and reduction reaction, we are going to try to find out what's called the oxidation number. And so how we find out the oxidation number, let's try to do an example, which is going to make it a lot easier for you to understand. So we're trying to find out the oxidation number of carbon. And we are going to be seeing carbon in the majority of this course, so it's going to be helpful to be able to know how to do so. So the first thing you're going to do is basically assume that the overall oxidation number of a neutral compound is indeed going to be 0. And when the carbon is going to be bonded to something more electronegative than itself, then it's now going to be given a minus N value. And the N value is going to be how many number of bonds with carbon and that electronegative heteroatom they're bonded to. Whereas when the carbon is bonded to something electropositive, it's now going to be given a positive N number. And with regards to hydrogens, they're always going to have an oxidation number of positive 1. And so when we actually count the oxidation number, this is able to tell us how the reaction is going to proceed and how many of the electrons of that atom the molecule is going to be sharing or losing or gaining during a bond. And so let's look at what they are basically doing when we look at methane. When we have methane, we have the carbon that's bonded to 4 hydrogens. So in this case, carbon is bonded to a more electropositive heteroatom. So therefore, when we look at the bonds that are sharing these 2 electrons, we're able to find out that the carbon is going to be basically causing the electrons to shift more towards itself. So in essence, in addition to its original valence electrons that it has, it's kind of bringing the specific valence electron from the hydrogen more towards itself. So it's kind of attracting that one. And therefore, we're able to now have that specific carbon that's now going to be gaining one of the electrons. And so we're now going to be causing that specific number to be -1 for each one of these electrons that it's gaining. And so because we have 4 bonds, we're now going to be having 4 as the oxidation number for carbon. And for hydrogen, we said that they always have the oxidation number of +1. And that makes sense because the hydrogen is indeed basically losing all of its electrons. And so it's going to basically have more of a positive character, is how you can see it. So when we have carbon as methane, we have carbon in its most reduced form. Because I said oxidation is loss, reduction is gain. So carbon has now gained all of these 4 electrons or 1 electron each from the hydrogens. I hope that makes sense so far. Now, if we basically then look at methanol, in this case, we're also trying to find the oxidation number of carbon. So if we look at this more in detail, we have the carbon that's bonded to 3 hydrogens, and we're bonded also to oxygen. And so if we look at carbon, we can see that if we have bonded to something that's more electropositive, then now we're able to see that the carbon itself is going to be gaining -1 from each one of these bonds to hydrogen, which means -1 times 3. But now it's also bonded to oxygen, which is more electronegative than the carbon. And that's why we're now going to be having +1 given off due to the bonding to oxygen, which means it's -3 plus 1, giving us the oxidation number of -2. And then when we look at formaldehyde, in this case, we're able to see that for carbon, likewise, we have the carbon bonded to hydrogens, which means that the carbon is going to be the more electronegative atom, and therefore they're now going to be having -1 from each hydrogens, but it's bonded to the more electronegative oxygen through 2 bonds. And so in this case, we're now going to have carbon have +1 for one bond and +1 for the other bond. And that's why if we add them all together, it's going to be +1 plus 1 minus 1 minus 1, which is going to be giving us the value of 0. And so that's how you're basically going to be calculating the oxidation number. And so by the end, on the carbonic acid, you can see that the carbon is bonded to 4 or 3 oxygens, but then one of the bonds is going to be a double bond. And so because carbon is bonded to only those heteroatoms that are all more electronegative than itself, then now carbon is going to be having +4 as its oxidation number, which is now going to be the most oxidated state. So if we actually simply look at this type of oxidation reduction reaction, we can also see it as oxidation that's now going to basically increase the oxidation number by causing the carbon to hydrogen bond, so something that was basically more electropositive than itself, then replaced by something that was more electronegative than the carbon itself. And so a lot of the times they are going to bind to halogens, but also oxygen is going to be more electronegative as well. And so when we basically have a C2X bond, a halide, oxygen, anything that's going to be much more electronegative is indeed now going to be an oxidation reaction. Now, and when we look at reduction, it's now going to replace something where the carbon was bonded to something more electronegative to something that's more electropositive. And so a lot of the times we say that when we have a carbon that's now going to lose its bond to oxygen or halides and now be replaced with a hydrogen bond, then in those cases it has undergone reduction. And so when we actually take a look at the previous combustion reaction, for example, when we looked at methane plus oxygen causing the production of carbon dioxide and water. This is also an oxidation reduction reaction, because if we look at carbon, we're able to see that it was in its most reduced state. But when we look at carbon dioxide, it's now going to be in its most oxidized state. So this has undergone oxidation. Whereas if we actually look at the oxygen's oxidation number, it's actually going to be 0 in the beginning. But then when we look at H2O, we're able to see that it becomes -2. And so as a result, this becomes a reduction reaction. So in a chemical reaction, something is always going to become oxidized and the other is going to be undergoing reduction. There's usually no case where they only undergo oxidation in one case and then the other doesn't undergo reduction. They usually complement one another. Now, when we look at an example like so, this is also showing us an oxidation and a reduction reaction. We're able to see that methane -4 is now going to become oxidized because it's now going to be -2. And the reduction reaction, indeed, here is going to be occurring when we have -2 and -4 with regards to its oxidation state of these carbons. So make sure you know how to basically calculate the oxidation number of these carbons or these molecules. And so when we look at the trend of this type of molecules, you can see that if we basically go off to the left side from 0, this is undergoing reduction. This is undergoing oxidation. If we look at it as a whole, this is basically undergoing oxidation from the left to the right. And I guess that is the end of the chapter. So take the time to review, and I'll hopefully go over some questions that you may have in the next class. So enjoy the rest of your day, and we will end here. Thank you for joining.